So hi guys, I'm here in the hippie room. I'm gonna start the lecture um, that I've told a few people I'm gonna do. I was gonna do, and I'm gonna do, and I'm trying to get the angles right for the camera here. Um, I told one of my friends or a couple of my friends I was telling about doing this lecture, and I said to them, I said, if I'm not nervous, I'm crazy because this is a lot on me right now. But you know what? I'm going to do it. I love it. Why don't we turn the computer so I don't have to change the angle of the thing so much? I'm trying to get a good view here of the board. I don't like that yet. Sorry about the... Oh, I know the board. It's because it's not straight up and down. Duh. I'm supposed to be the math guy. And, So how you guys doing? Love you guys. Peace, love, and rock and roll. This side. So I'm going to start the lecture. So let's get some background here. I went to Harvard College for 3 years. I was an engineering major, and I just dropped it cold turkey when I left. I just divested rather than investing. I divested. I just did anything but engineering. And then I went to my music again, and now a bunch of years later, I made a connection between, or I'm making a connection between higher math and music theory, or at least something of that sort. So just bear with me. Hopefully we can do this. I only have colors blue and green. My black and red are worn out. They don't work anymore. So that's the two colors I have left. I think I'll use blue. Why not? Anyway, let's just get started. Systems engineering uses a lot of analysis of signals, which are basically oscillations through time of a value. Let's say intensity over time. It could even be intensity over any other variable. It could be intensity over space or intensity over distance, but whatever. But a lot of times it's intensity over time. And a lot of times the intensity can be what you would call aperiodic, means it just goes on, just some pattern and doesn't repeat, and it just goes on. And it can be defined into a certain area. They call that contained, or it can go infinitely. But the signal just meanders, and it can still be a function because there's only one y value for x value, but it would be called not a periodic function, or aperiodic. And if it's not periodic, it technically means that the frequency is infinite, actually, if you get my drift, because frequency equals 1 over the period, or time, or t for period. And if something never repeats, it has infinite period, because it takes infinity to repeat. So the frequency would then be f equals 1 over infinity. And we all know that equals 0. Wait, wrong. I did that wrong. Let me start over. Okay. Oh, I know what I know to do. I know what to do. Wait. Yeah. Oh no. Here's how I look. No, here's how I look at it. No, I'm not going to look at it that way. I'm going to look at it this way. If it's aperiodic, then actually the period is 0. It's the opposite of what I just said. It only repeats every dot at a time. Only each dot is its own self. So in an aperiodic function, the actual period is 0. T equals 0. It repeats itself only at that point. So what does that mean for the frequency? Frequency equals 1 over t. An aperiodic function has a t of 0, so frequency equals 1 over 0 equals infinity. So basically, a signal that doesn't repeat or aperiodic is actually a signal that has an infinite frequency. We can't deal with infinity very well. It doesn't make much sense, so we call it aperiodic and don't deal with it. But for signals that are periodic, they repeat a pattern in time. From here to here is the same as from here to here, and it goes on forever. or even contained, but at least it's periodic. It has a repetition point along the way. And we call that periodic functions. Now, here's the deal. That is a periodic function. The deal is going to be, a lot of the deal is going to be, I'm going to use a sine wave, okay? And why do I say that? Or a cosine wave. Why do I use that? Why is that periodic? Well, in trigonometry, you have a hypotenuse, h, and you have a x and a y, where x is horizontal, y is vertical. And the angle, it would be like here, and the cosine is EJ. It would be x over y. I mean x over h. This part over this part, and then the sine would be the other thing, y over h. This part, the vertical part, would be so basically cosine of some angle theta equals x over h. And if h is 1, then that's just x, and it's just the x coordinate, or the horizontal coordinate. And then sine theta is y over h, and if h is 1, that's just y. So sine is the up and down part if the h is 1, or they call it unity. So believe me, I'm getting somewhere with this. It just may not. If it doesn't look like it, well, then maybe don't watch. But I'm telling you, it will go somewhere. This little lecture, at least that's what I'm going for. So what do you have? What do you have that relates sine and cosine functions to periodic things? Well, if you have a circle, make it a unit circle. Like I just said, radius is 1. So radius is 1. 1. Radius is 1. You have that. If the angle's here, you have that. If you watch the cosine is the horizontal part, and if you watch the angle starts at 0. 0 angle is here, and then the angle goes that way to be positive. So if the angle moves like this, notice how the x part will move along the way. It'll start at 1 because the angle is 0, and then it goes back towards 0 as the angle gets bigger. It goes back. This part is going to change to get bigger. Finally, it goes back to 0, or up to 0, and then it goes all the way back around to -1. Then it goes to 0, and then it goes to 1 again. So the way to map periodic functions fundamentally is circular motion. And then on the this cosine thing, cosine theta, will be a periodic function because it just goes around and around the circle. And the same is true of the y. Y, the letter, not WHY. The y part is a sine. It starts, so the sine part, that's this part, the vertical. So it would start at 0, and then as it goes, as the angle gets bigger, it goes up toward 1, and then it goes fall back to 0, then to -1, then to 0. So the sine of theta is periodic also. It's just like I said, y over h, but h is 1, so it's sine and cosine are periodic motion around a circle. We have that so far. So there we go. We're getting somewhere. Now, what circle am I talking about? What circle is there that I'm going to have periodic motion around? Well, you have numbers like real number line. You have 0, 1, 2, all these numbers. That's fine. Number like 5. It's called a real number. It's a one-dimensional axis. But what if I say I want my number to be the square root of -25? Well, that is square root of -1 times 5. What is square root of -1? It doesn't exist. We'll just call it I. So this I equals square root of -1 doesn't exist. We're going to call it that. So this square root of negative 25 is actually 5i, which is an imaginary number. Okay. Any multiple of I, which is a square root of 1, is an imaginary number because we just made it up. It doesn't really exist. No number when multiplied by itself equals a negative number or negative 1. So the square root of negative 1 is an imaginary number. So so now we're getting ready to have something called the complex plane. It's been called the Venn diagram, or the I think it's called the Venn diagram or the argon plane. Oh, and that's chemistry. Argon diagram, or the argon complex plane, argand diagram, something like that. It's where you have now, if you have numbers that are real, like 5, and numbers that are imaginary, like 5i, the next thing to do is to add them up, make a number that has both a complex part, a real part, and a complex part. I mean, a real part and an imaginary part. So we call such a number a complex number, like such as 5 plus 5i. It's got a real part and an imaginary part, and therefore we call that a complex number. Now, usually, to plot it the diagram of it, you need two dimensions, because one dimension is the real axis and one dimension is the imaginary axis. So we use the horizontal, the x-axis as the real axis, and then we use the y-axis as the imaginary axis. So if I call z a complex number is x plus iy, it's got the real part, which is x, and the imaginary part, which is iy. That's z is a complex number. X is the real component, and iy is the imaginary component. Or you can just say y. Yeah, iy is the imaginary component. So, how do you plot one of these numbers on what's called the complex plane? Well, if this is 5 and this is 5 in this way, this would be 5. This point here would be 5 plus 5i. It's just called the complex plane. Not line, the real line, the imaginary line, but the complex plane, two-dimensional. So now what's the next step? Make a circle. Maybe have a circle of radius 1. We like that. And as the motion goes, starting with an angle of 0, if you start here, the angle, the theta of the angle, it starts out at it's going to have, as it becomes two-dimensional, the x coordinate of this point of this complex number is going to be cosine. Can't even write an s. Cosine theta, and the y part will be sine theta. Okay, fair enough. So if I write a number here, x plus iy, you see that the number can also be written, z equals x plus iy, can be written like this. It can be written as z equals cosine x plus I sine y. No, sorry, not y. Theta, the angle. Yeah, sorry. Z equals cosine, write the s again, cosine theta plus I sine theta. That is z, the complex number on this plane. If I make r a different number, you have to put an r in front of everything, but to make r1 is easier. It's called a unit circle. Circle of radius 1. So z equals cosine theta plus I sine theta is a complex number. Now, here's where we're going to do something. We're going to do something here. This is so far we have z equals cosine theta plus I sine theta. It's a periodic complex number. See, that's the thing. It's sine, the real part, x, and the imaginary part, iy, would move funny. Like I guess x starts at 1, so x would start at theta, it would be 1. And then it would go to 0, and it would go -1, 0, like maybe that far. And that would be the cosine theta, which is the x part, the real part of the periodic complex number, a variable. No, right. The sine part starts at 0, the imaginary part, and it goes up to 1, down. Wait, it goes like, yeah. Well, that's that. I made that marker on there, didn't I? The mark would be over here. That's the periodicness of it. Yeah, that's the periodicness of it. This would then be up to wait, let's see, 1, and back up to here. And this would be here, and then here, up, down. Yeah, that makes sense. Yeah. So this would be this would be theta equals 0, and then the theta equals pi over 2, theta equals pi, theta equals 3 pi over 4, and then theta equals 2 pi, which is also 0. Whereas a sine goes yeah, it goes like, yeah, there you go. Yeah, it goes like that. So while the cosine is doing this, the sine is going, oh, I'm going to do that a little better. Like that. See that? So it matches like that. So then this is y equals I sine theta. Yes, y equals I sine theta. So they're both so the real part of the variable is periodic, and the imaginary part of the variable is periodic, and they have this relationship on the complex plane. Now I'm going to do one more. I'm going to do a little thing here. I'm going to bring in a number called e. E is stands for, it came from Euler, I think, or exponential. E is a number that's an irrational it's an irrational what do you call it? I think it's an irrational existential constant. I think they call it that, existential. It's irrational and it's existential. Its value is approximately 2.718281828, but it doesn't repeat like that forever. It just looks like it's going to, but it doesn't. I can't even write an 8. 1828. Okay. Existential irrational number. And this is an interesting number. I'm going to go on about it quickly before I go apply it to what I've been talking about before. In calculus, you have a function that and in calculus, the derivative of something, the derivative of a function is how fast that function is increasing over time or decreasing over time at that point. So if I have y equals e to the x, what's that? Well, this is the x, this is the y equals e to the x. It turns out that the derivative dy dx of e to the x equals e to the x. The derivative, which is how fast it changes at any point, is equal to the function itself. So you have a function which, whatever the value of that function is, that's how fast it's increasing. So if the function right here is, if the function here, back here is 0, it's increasing by 0 because therefore it would be horizontal, because a horizontal line has 0 slope. A vertical line has infinite slope. In between, that would have one slope, and so forth. So if when x equals negative infinity, e to the x equals e to the minus infinity equals 1 over e to the infinity equals 0. So at x equals negative infinity, which is back here, the function is 0, and therefore the derivative of the function, which is the change of the function, is also 0, which means it's horizontal. And then as it goes further into x getting more and more positive, it does this kind of thing. At any point, y equals e to the x, the rate of change of the function is equal to how much the function really is. At x equals 0, the function would be y equals e to the x is y equals e to the 0, which is 1. So right here, the value of the function is 1, and the slope of the function is 1, because that's what it has to be y derivative of e to the x equals e to the x. And then as x becomes infinite, x equals infinity, the function is e to the x equals e to infinity equals infinity, which means the function is the derivative of the function is infinity, and infinite slope is straight up and down. So as it goes up to x equals infinity, it goes higher and higher until it goes straight up, and that's called exponential function. This number e, I'm going to erase this. I think you guys get this. This is cool. This number e is the number such that if y equals e to the x, then dy dx, or some people call it y prime, equals e to the x. And that's one way that e can be defined. Yes, there's another way to calculate it with calculus and all that. I'm not going to go into it. You can read it in any single variable calculus book. I'm not going to go there right now. You find out, and it just turns out that this e equals 2.1 2.718281828, and it goes on, but doesn't repeat that anymore. Okay, fair enough. Now, there's something called Taylor series, where e can be broken down into Taylor series is a infinite series expansion of the function. So e to the x is a Taylor series of certain. Series is a number of is a bunch of terms added and added and added if it's infinite forever. And then you can do the cosine x Taylor series and the sine x Taylor series. And it just so happens, according to Taylor series, the e part has odd and even both terms, and the cosine has either the even or the odd, and the sine has the other one, even or odd. It turns out, just from Taylor series, that you can prove quickly. I won't go into it. You can find it in a complex variables or complex analysis book. Turns out that e to the I theta equals cosine theta plus I sine theta. It turns out that just happens to be true for e equals 2.718281828 and so forth. That's therefore you have this formula, which is called Euler's formula. Very cool formula. So why do I go on about this? Because this is why. I'm going to go back to what we started talking about at first, when we had the complex plane. I had the circle, and I had the real part is the x part, the y part is the imaginary part, and it turns out that if this angle is theta, that e to the I theta equals cosine theta plus I sine theta, which is Euler's theorem. So a function that's a function of theta, the angle, going around and around a complex plane is equal to this, e to the I theta. And it's equal to this, which is called Euler's formula. Now, what we're going to do, something. This may sound like, what's he doing? I'm going to leap now. I'm just going to leap into faith, or what do you want to call it? I'm going to leap to I'm going to leap to music theory for a second. Okay, we're going to go there now, and then I'm going to try to tie things together. So, what is music theory? What is music based on? Well, music is a graph of intensity over time. So this is time. This is time. This is intensity, height, or power, or whatever. And strings vibrate at sine, cosine frequencies, and I'm going to get into that in a minute. And if I have if the frequency repeats in this much time, that's one of that's called a period t of time, and the frequency equals cycles per second. If this is time, how many cycles happen in a second? That's frequency. And frequency is equal to 1 over t, because when you say per, it usually means to divide. So frequency equals 1 over t. It's the inverse of the amount of time it takes per one cycle. Now, a couple things here. First of all, if the frequency gets big, like maybe a big frequency like this, bigger than this one, then if the period gets big, it takes longer to make a cycle. So the period is bigger, then the frequency is 1 over a bigger number, which is going to make the frequency less. So a big period makes a little frequency, because the frequency goes down as the period gets higher. Inversely, as the period gets smaller, you get the frequency is 1 over a small number, which makes the frequency bigger. So short periods make big, high frequencies. Big periods make low frequencies. So period and frequency are inversely related. So there's that so far. So now what I'm going to do, I'm going to look at literal vibrations. Like, let's say I have a string here. Okay, the string has a length, or whatever. Three things affect the pitch of a string: length, thickness. I'll just write it out: length, thickness, and tightness. How tight it is, how thick it is, how long it is. If thickness and tightness are kept constant or time invariant, TI, we have length as the main variable. Just keep the same thickness and the same tightness, but just look at the length. So then length would be the variable here. This is the length. Now, what is the length would be like the period. Length is the amount of thing that it has to vibrate in. So if the length is this much, and you can see that one of the periods will be, it will cycle once in that length. And if this length is L, then the frequency is 1 over L. And if L gets really big, the frequency is less. That it makes a lower pitch. If length gets shorter, the frequency is higher. I mean, length is shorter, the string is shorter, the frequency goes higher because 1 over a smaller number is a higher number. So short length, high frequency. Long length or big length, low frequency. So far, I think we're hanging in there. So what you have here is, this is a concept here. So I'm going to do frequencies analysis. We could call it that. So I'm going to have a length here like this. Here's a length. Now, here's the thing. I said that the lesson was going to be about overtones and undertones. Now, what is that? Well, this is a length of a string. Before I go into this, there's a thing called there's a fundamental period. If I have a lot of things going on here. Okay, dun. There's a fundamental period. The fundamental period is the shortest period that is a period of it. Do you understand that? If this is my wave, this is the fundamental period right here, because it's the smallest period you can have. But guess what? Double that length is also a period. This is also a period. Erase this part here. This much is a period, but so is this much, because it's also periodic in this way. This function is also periodic in that length. Oh, wait, it's also periodic over here. So it's another period, which is of a periodicity, is this much. Oh, wait, it can go that far too. So another period is up here. So there's only the smallest period is called makes it the fundamental period, is the fundamental period. Every multiple of the fundamental period is also a period. So if this period, because if this period is T, or call it L, we'll just call it T. No, yeah, let's call it T. This period T is only half the period of this period, which is also a period of it. But this period is twice this period, so this next period is 2T. But 3T is also a period, and so is 4T. So any multiple of the fundamental period is also a period. The smallest period is called the fundamental period. Now, so far, so good. I mean, people might be bored with this, but the notes don't watch it then. I'm good. LOL. So we have a string of a certain constant tightness and thickness, but variable length. And one more thing before I say that. So T is a fundamental period, but also 2T, 3T, for any multiple of the period is another period. So the period, you could call it little t, because it's not the fundamental t necessarily. The big T is the fundamental period, but the little t equals NT, not TNT, LOL. Any number times the fundamental period is also a period. So how about frequency? How does that affect the frequency? Well, frequency is 1, you can't even write, is 1 over T. What I'm going to do is I'm going to call the fundamental frequency, because this isn't really this isn't really correct here, but it's true. Frequency is 1 over T, but I'm going to call the fundamental frequency is 1 over the fundamental period. Get that? So since the period fundamental since the fundamental period is the smallest period, then the fundamental frequency is the highest frequency. Wait, let me think. No, wait. Yeah. Fundamentals. Wait. The shortest frequency. Yeah, wait. Highest frequency. That's true. The fundamental period is the smallest period, so the fundamental frequency is the highest frequency. Wait, is that true? The frequency is inversely related. Length, frequency, length. The length gets wait a second. The fundamental, if it fundamental period is the shortest period. As frequency. Oh, I get that. Yeah, that's right. Yeah. Yes, I get it. So the fundamental period frequency is one over the fundamental period, which is the highest frequency that you can have for a wave. The frequency is 1 over any period. 1 over, so little f is 1 over little t. Any t can be any multiple of t, capital T, can be another period, but it's a bigger period. Therefore, these frequencies of the unfundamental periods are lower frequencies. So, and that's true. But the highest frequency is the fundamental frequency, which is 1 over the fundamental period, which is the shortest period that it vibrates in. So what does that mean? What that means is I have a string, and it's got frequencies going on like that. So the fundamental period is the smallest period, and I'm going to call this 5. Oh, let's call it 4. This would be better. Okay, that's 4. That's the fundamental. That's the smallest period. So the frequency of that would be 1 over 4, because T is that frequency is 1 over 4. So that's the fundamental frequency, right? But this string also vibrates at 8. T, little t equals 8. That would make little f equal 1 over 8, which is half the frequency of 1/4. So as we double the period, we have the frequency. So the same wave is multiple different types of periods, where each period is bigger than the fundamental, but yet also more, a fundamental frequency and other frequencies that are lower frequency. Because if I double the period or the length of the string, I get half the frequency. Yeah, I get that. So what we're doing is, if I have a string, let's see if I can figure this out here. If I have a string and yes, the length of the string, here's what we can do. So we've got some background here. So now let's have a string again. Let's have a string. Now, here's our string. Here's the length of it. Now, if I can't really make the string longer, though, can I? If this is a string of length 10, I don't get to make a string of length 20 out of it, because there's no string of 10 is the largest length I'm going to have with this string. So while I double the length to get half the frequency, that doesn't exist in nature. It doesn't exist in real life. There's no string of 20 there to give half the frequency, or lower frequency by factor of half. Or there's no string of 30 length to make 1/3 the frequency. So these imaginary strings that are multiples of the length of the first string are all theoretical, but don't exist in nature. If you had a string of 20, it would be half the frequency. If you had a string of 30, it'd be 1/3 of the frequency. But the string has a limit, only be 10 length, 10 inches or feet or whatever long the string is, and that's all you get. So these imaginary multiples of the frequency are called undertones, because multiples of frequencies that where the length goes up by 2 or 3 or whatever, the frequency goes down. So because the frequency goes down, they're called undertones. And undertones don't exist in nature. If I have a C, and then I have and I make the string length, I double the length of the string, I would have a C C -1, a C that's half the frequency of the first C, because the imaginary length went up by 2. The imaginary frequency would be half that, and half the frequency is an undertone. So here you have a C. Let's say this is a C right here at this frequency. Here's C, and then I would have another string could be 20, which would be twice the period or half the frequency. And if it's half the frequency, let's say it would be a lower note. So if C were if it's a staff and one of the notes is here, the lower note would be an octave under the original note, and that's called the first undertone. So if I have C, let's call it C3, then C2 is the first undertone, because doubling a pitch happens to make it the same pitch. We don't know why in music that's true. When you double a pitch in music, it sounds like the same pitch you started with, just a different register. So what the imaginary double length string would have imaginary undertone of half the frequency, because it's double the period, half the frequency, which would be an undertone below the original C of the string length of 10. Now, what about the 31? Well, if I triple the length of the string, I make the frequency 1/3. And that's another undertone, but instead of being half the pitch, half the frequency. So if this frequency is 440, it's not C, but let's just pretend. The half would be 220. Let's not make that, because that's confusing, because that's an A. And I know a real C is 256. So let's just do that. C could be 256. Then half the C would be half of that, which would be 1, 2, 3. No, come on, Jim. 2 is 1, 2, 8, 128. That would be the first undertone, and that would be another C. Then if I have a theoretical string 3 times the length, that would be 1/3 the frequency of that. And 1/3 of 256 is 256 divided by 3, which is 8, 168 and 3/16. 8. Wait, a third of that. A third. How do you divide 3 into 256? That would be 8, 16, 8, 16, something like 80, something like 85 or similar, something like that. And what pitch does that make? Well, a pitch of 85, or 1/3 of the C, would be an octave plus a fifth. So now this would be a fifth down, fifth. So if this were C and this is C2, a fifth below that would be F, G, A, B, would be F. Would be an F. Let's say F2. Okay, F2, because a C, D, E, wait, a fifth below would make F to C a fifth. F, G, A, B, C. And now you make the string 4 times longer. You get 40. We'd have 1/4 the frequency. It's even lower. 1/4 is half of 1/2, so it's a double octave. So you didn't have another C underneath. C1 would be the next undertone. How about 5? Well, 5 with 50 would give you 1/5 the frequency. 1/5 down would give you a fifth is an octave and a major third, so a fifth and an octave. So you'd have a major third. You'd have a major third below that. So this would be now, and a major third below C would be A flat. Let's see, I'm write this better. Underneath, did I do that right? Yeah, would be A flat. 2. So dun. Oh, I did have a C2, didn't I? And then A flat would be A flat. Wait, no, I didn't. C, F. Yeah, no, that would be A flat 2. Yes. And A flat would be a major third below the F. And that would be, this is original 1, 2, 3. Wait, 1, 2, 3. Let's see. Oh, yeah. C, F, G. This is the original. This is 2. This is 3, 4. Oh, yeah. Oh, yeah. You do have a C1. Yeah, because the double octave. I forgot the double octave. Yeah, the double octave is C2. And then below that double octave would be a major third below that, which would be A flat 1. So it's an A flat 2 octaves plus a major third down, which is an A flat below the double octave below the C. And so that would be and that would be the fifth. That would be the fourth undertone or fifth partial. Partial includes the first one. Overtone doesn't. So first partial is C. Second partial, an octave down. Third partial, an octave and a fifth down. Fourth partial, 2 octaves down. Fifth partial, an octave and a major third down. So it'd be an A flat underneath that C. And then you could do the sixth one would be 2 octaves and a let's see, C6. 6 is let's see, 6 would be 6 over 2 is 3. It'd be a fifth under, 2 octaves and a fifth under. So that would make it another F down there. It would be I think, wait, F, G, A flat. Yeah, another F. Yeah, another F below the A flat, which would be F, G. Wait, a minor third below this A flat would be an F. This is an A flat. A minor third below the A flat would be an F, and that would be number 6. That minor third below would make it A flat F. It would be 2 octaves and a fifth down. So 2 octaves would give you C, and then a fifth down from there would give you an F, F, G, A, B, C. So that 6th partial would be 2 octaves and a perfect fifth down, which would be an F under that A flat. So now, so these undertones, this is, I'm going to write a little better here. I think we explained that, but now I'm going to write it a little clearer. So basically what we're talking about with the undertones is you start with your top note, C. That's the fundamental frequency. Then the next partial is a C below that. That's double the length of the string, but half the frequency. Next, triple the length of the string, but half the frequency would give you an F. that's I'll call this, like I said, C3. This is an octave. So this is, all right, octave. This is a fifth. Okay, that's the F. Then your next one is a double octave of the C. So that's a C1. This would be F2. That would make this a fourth, because a fourth and a fifth make an octave. And then finally, and then the next one would be the A flat, and that is right here, A flat 1, and that's a major third. And that, and finally the F would be 2 octaves and a fifth down, which would be F1, which would be, this would be a minor third, because a minor third and a major third make a fifth and a fourth make an octave, the F to the F, and also the minor third and the major third make a perfect fifth. Then this perfect fourth, along with this perfect fifth, make this octave, and then finally this octave is its own thing. So what you're saying is that undertones don't exist in nature. The string doesn't get to be longer than it is, so the imaginary tones that are under it, which would be if the string were multiples of the original length, are called undertones, and they're only theoretical. But what's interesting about these undertones, let's write the F down here. And, I did that. Wait, A flat. 1, 2, 4th, 5th, major third, minor third. Oh, okay, A flat. And then C, F, yeah, A flat. 1, 2, 3, 1, 2. Oh yeah. This major third, minor. Yeah, this is, yeah. All right, this is the A flat here, and this is the F down here. Okay, that's right. This would be A flat 1, and this would be F1. So what's interesting? So basically, I have F, A flat, C, F, C, C. Now, what's interesting about it is if I took it from here down, it would be like an inversion of a major triad. But because we don't take chords from the top down, we take them from the bottom up, we're going to take it from down here. And what we just said, that's an F. So the next note up would be an A flat. So now I have, from going upward, I have an F going up to an A flat. Then what's next? I have an A flat going up to a C. Then I have a C going up to an F. Then I have an F going up to another C, and then an F going up to another C. What's that? That's an F minor triad generated by a C. So this F minor triad is based on undertones that don't exist in nature. So the F minor triad is derived from the C, but doesn't exist in nature. If you play, so the minor triad is a synthetic chord. It doesn't appear in nature. You're not going to hear a minor triad in any one sound in nature. But we'll just call it. We'll just make it up. It's the undertones, but taken from the bottom up. And a C starting note generates an F minor triad. So the F minor triad, the minor triad is a thing that doesn't occur in nature. Yet we call it such. So let's do, that got caught in there. So let's do one little trick, and then we're going to do the overtones, and we're getting closer to the end. We're getting closer to wrapping this up. Okay, so if I have F minor equals F A flat C. I wrote that very badly. That's kind of a little rhyme. What's F major? That's F A C. So another way of I better charge my computer. My computer's battery's running low. I'll be right back. I gotta plug my PC in because my battery's low. I'll be right back, I promise. Be right back. better plug my computer in while I'm here so it doesn't die on me. Let's do that real quickly. And we're plugged in. All right. Hope I didn't change that. Anyway, that's okay. And you guys is in. All right. So another way of looking at, the F major triad does exist in nature. The F minor doesn't, but yet if you look at it from the same starting point, a major triad is a minor triad with the third up a half step, and the minor triad is a major triad with the third down a half step. So there's that interesting absolute kind of looking at it, where major means major third out before underneath the minor third, and that's occurs naturally in nature, and the minor triad means a minor third under below the major third, which does not occur in nature, but yet we make it up. Finally, here we go. That was the undertones. It gets easier from here because now we're in actually things that actually do exist in nature. Now let's take the same string again. 10. Let's make it 12 this time, just for the heck of it. Its length is 12. 12 feet, 12 inches, whatever. That's our string in real. It has the same thickness and tightness. Thickness and tightness as all the other strings, but it has a length of 12 that can be varied. Now, what happens? Okay, a string of length 12 will vibrate at the fundamental. Well, it'll vibrate at one cycle for that string, and that's the fundamental. If the string is G, then that's a G note. That's just a G. Let's say that's a G. Okay. But what happens in nature? Imagine that string there. This is the biggest. This is the biggest period that this string can vibrate at because it's the longest it is. So the big period, if frequency equals 1 over period, and the period gets smaller or is as big as it can be, then the frequency is as low as it can be. Ooh, this is the lowest frequency that 1 over 12 is the lowest frequency that string can vibrate at. And that's why that lowest frequency is called the fundamental. In this case, let's make it C again. Well, let's not make it G. Let's make it C. So I have C, fundamental. Largest length, which is largest period, which is smallest frequency. It's the smallest frequency that this string can vibrate at, and we'll call it C. All right. So what happens after that? We'll just put a C here. Well, if this string vibrates at 12 and it's periodic at 12, it also vibrates at half that. It also vibrates at 2 cycles for that 12. So it also does this. It also can vibrate at 6 as its fundamental period, but 6 is half of 12, so it still has a period of 12. But the fundamental period of this node is actually half that, or 6. Half of the 12. And if the frequency is halved, I mean, no, the period is half. The period is half. If the period is half, the frequency is doubled or twice. So that means that this string will vibrate with this period, which makes, since that period is half that one, this frequency is twice as much. So that's called an overtone because the frequency is twice the frequency you started with. So that's another C. Maybe I'll write the C down here. C1, and then this C2 is this C, an octave, twice the frequency, half the period, because half the length, but twice the frequency, so it's another C, a C above the fundamental C, which is an octave above, and now we're talking overtones. Think period gets smaller, frequency goes up. Overtone, first one, is the same note as it started with. We don't know why that is, but we'll just call it that. So that's a C, an octave higher. Oh, but wait, this string also vibrates at third multiples too. So it also goes like that. That third that would be a third of the length. So that would now be 4. And don't be 4, be after. No, just kidding. But that before is a third of the original length. So the frequency would be 3 times it, because frequency is inverted from period. So that would be a string, a note that's 3 times this first frequency. And what's that? A note 3 times the frequency is an octave and a fifth. So that would now be a G. I'll call it a G2. Now it can also vibrate in fourths. It can go like this. And that one fourth of the period makes 4 times the frequency. That's a double octave. So now at 4 times, you have a C up here. C3. Okay, then what about 5? It can vibrate in 5 length. 5. I don't know if I'm doing that right. 1, 2, 1. 5 times. A fifth of the length makes 5 times the frequency, and that would be 5 times the frequency is 2 octaves and a fifth. So that would now be CG. No, wait, let me get that right. No, not a fifth. A third, 2 octaves and a third. Yeah, 2. That's right, 2 octaves and a third. I'm getting tired. So fifth makes 5 times the frequency makes 2 octaves and a third. So that would be an E up here. E3. A fifth of the length is 5 times the frequency, and 5 times the frequency is 2 octaves and a major third. So that would be a C. How about 6? I can multiply it in 6, and that would be 2 octaves and a fifth above. So that would be a G up here. And that's another overtone. So the first partial, C1, second partial, octave higher, C2. Third partial is an octave and a fifth. Fourth partial is 2 octaves. Fifth partial is 2 octaves and a major third. And sixth partial is 2 octaves and a perfect fifth. But now what do I have? What do I actually have now? What am I getting at here? What do I get? These are called overtones. They exist in nature. They do exist because a string can be vibrated at factors of its length, which will be doing multiples of its frequency. So the original one is C. Then after that, I got another C. Then let's make it a little wider. Sorry about that. Let's make a C. Then I got another C. Then I got a G. Then I got a C. Then I got an E. And then I got a G. All right. This is octave. This is fifth, fourth, major third, minor third. Same thing I had with the undertones, only these really exist in nature and they go upward, not downward, and they start with where they start, not underneath. So what's C, G? Well, C, C, G, C, E, G is called a C major triad. Okay, and C major triad is C, E, G. C minor does not exist in nature, but that would be C, E flat, and G. Half step difference between the third. Minor triad has a flat third, and major triad has a major third, which means minor triad is a major triad with a flatted third, and a major triad is a minor triad with a raised third, a sharp third. So a little background on math combined with some music. You could analyze this really far. I mean, I'm just opening up the doors here. I mean, I'm not doing, no pun intended, possibly being Jim Morrison's son of the Doors. The son of Jim Morrison of the Doors. I'm not of the Doors. Interesting stuff going on there. You have frequencies with complex numbers and Fourier transforms and overtones, undertones, because it turns out that, back to math now, here's where the engineers are going to get their kick here, I hope. See, the thing is, back to math now, any function that's periodic, And let's go like da 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 da. Now let's go like da 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 da. And let's go like da 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 da. It's periodic, but it's not a perfect single frequency cosine wave or sine wave or whatever. What does it have though? Think about it. The overtones exist, the undertones don't. So any function of frequency, let's in math, let's call it by radians. So cycles per second is just 1 over t. Let's do that first. We're getting there, guys. Cycles per second is 1 over t, but what we often do in engineering is do radians per second. And since a cycle is 2 pi radians, one cycle equals 2 pi radians, because one circumference around the circle is 2 pi, because the circumference of a circle is 2 pi times the radius, and a radian is how many radians does the arc of a unit of a unit circle of that transcribe around the circle as you go around the circle with the angle. So if one cycle equals 2 pi radians and the frequency is 1 over t, then if you have if one cycle is 2 pi radians, then a frequency in radians would be, instead of cycles per second, would be 2 pi radians per second. See, because if frequency equals 1 over t, and one cycle is 2 pi radians, then omega, which is angular frequency, is 2 pi over t. I wrote that terribly. 2 pi over t is omega, the frequency in radians. So let's do that for engineering's sake. We have to make that leap of faith, or leap into faith. So for now, our frequency is omega, and we said before that e to the I theta equals cosine theta plus I sine theta in engineering, in math. Well, what is, if theta is an angle and the angle is moving, it has angular velocity, then what is, if omega is angular velocity, then it is d theta dt, the rate of change of theta in time, which is 2 pi over the period, fundamental or otherwise. So if this theta is 2 pi, if omega, if theta is the 2 pi and omega is 2 pi over theta, let's work this out. If omega equals 2 pi over t, then theta, which is the angle, is cross multiplying, which is kind of a silly thing to say though, omega t. I think omega t. Yeah, that's right. Omega's omega t. Theta. Yeah, I didn't write that very well. Theta equals omega t. Wait, I didn't write that very well. Let's start over. If omega equals 2 pi over t, and 2 pi is the angle, then 2 pi equals omega t, and 2 pi is the theta, because 2 pi is an angle. So theta equals omega t. Little t if I mean any period, and capital T if I mean the fundamental period. Got that so far? Theta equals omega t. Fair enough. Now we know that much. Let's go back up here and say e to the I omega t equals cosine omega t plus I sine omega t. All right, got that. E to I. All right. we call, but in engineering, I is in math terms, we could call current C, but Einstein's theory, E equals mc squared. C is the speed of light. So we can't call current C, we have to call current I. So I is current in engineering, whereas C is speed of light. So we have to call this I something else. We call it J. So we call, since I is current because C is the speed of light, J equals square root of -1 in engineering. In math, we just go ahead and use I, but I'm an engineer. At least I was. I was studying the E to the J. Yeah, I can just write E to the, start over. E to the J omega T equals cosine omega T plus J sine omega T. And that's the functional version of the Euler's theorem that's used in engineering. We have that. So that's a cool formula. All system engineering either is based on that or comes from it or is added to it. Now, what do I do with that? What's the next step I'm going to play with here? One last thing I think we'll be done. So notice the T I wrote, I didn't make it always clear, did I? About the T, little t versus big T. But let's make that clear now. So I have this function that's periodic, but it's weird. It's not straight, simple. It's strange stuff, you know? So what happens is the engineers tune up. This is what's happening in engineering for engineering people. The longest period, which is the smallest frequency, smallest omega, is the fundamental frequency, or fundamental, or the fundamental frequency is equal to 2 pi over the fundamental period. And I can call that omega. I don't know how they do it. Omega, what would that be? Omega, a big W. I don't know. The biggest period makes the smallest frequency. So the smallest frequency is the fundamental, the one you start with. So there's that. But then there's also a frequency that exists here where the period is half that. So here, T equals 1/2 of T. So if T is 1/2 of T, if the little t is 1/2 of big T, then if the little t is 1/2 of that, then the frequency is twice that. So that would be an overtone. It would be 2 omega. Twice the fundamental frequency is also a frequency that the thing vibrates at. So far it vibrates at omega, 2 omega. And of course, you could have a frequency, you have a third of that vibrating, and that would make a third of the period, but 3 times the frequency. So this function that's periodic is periodic at the fundamental frequency, but also every multiple of that. So here's the thing: the frequency omega, the frequency. I don't know how they do the fundamental frequency. I'm going to call it just omega circle. I don't know. Fundamental frequency. I mean, wait, that's fundamental frequency. Oh, I get it. You don't care about the fundamental frequency is just one of the frequencies, but the frequencies you have available are 2 pi over would be T, but it's any multiple of that. So it's n times 2 pi over t. Yeah. The frequency is the fundamental frequency, which is 2 pi over the fundamental period, or any multiple of it, times any multiple, any number that's where n equals 1, 2, 3, not, so on. So the frequency is 2 pi over t, 2 pi over t times 2, 2 pi over t times 3, 2 pi over t times 4, and so forth, on and on. All overtones, all multiples of the fundamental frequency, which are all overtones, because the periods are getting smaller by factors, while the frequency gets larger by multiples. See that? So the what you're going to find in engineering, and wipe all this away now. I hate to do that because it's beautiful work, some of it. At least it looks to me. You have that any frequency of time, function of time, a function of time that's periodic can be expressed as an infinite sum of n I'm going to call it f of omega, but maybe make a different funny thing on top of it. Any multiple, there's a component that is for the fundamental period, for the fundamental frequency, and any multiple of it, there's a component of sine waves and cosine waves that corresponds to that. A Fourier transform is simply what values of each of those multiples of the fundamental fundamental frequency are there to make that particular function that we started with, the weird thing. But no matter what, if you assign the right values to each of these frequencies, multiples of the frequency, you can get the original function. In fact, you can do what's called a frequency domain, f hat of omega, where actually you're not even you're thinking of the function in terms of pieces of multiple of the fundamental and any multiple of it frequencies, but at different amplitudes of each to get you that original function. And that's how and this function right here is called the Fourier transform. The frequency domain of a time domain function is called the Fourier transform of that original time domain function. And what's interesting about systems engineering from there is that you have this kind of thing. You have f of t back and forth. That's awful writing, dude. Yeah. F of t back and forth between f hat of omega. Time domain, frequency domain, Fourier transform, inverse Fourier transform. You can go from time domain to frequency domain. It's called the Fourier transform. The frequency domain to time domain is called an inverse Fourier transform. Do the math. It's an integral. It's math. It's calculus. It's all that good stuff you can find in any systems engineering book worth its salt. And I know Harvey Mudd books are the best. I had a great book. I had great books there. I read one called Signals and Systems. I forget who wrote it, for E101 in Harvey Mudd College for first semester of my junior year, E101, read book called Signals and Systems by somebody. So why is that important? Because if I have a signal input, I don't know the symbols as much as I used to. Input, let's call it input of t, and then I have a system. Call it h of t. And then I have an output. I'll call it O of t. Yeah, I'm doing that right. All right. So this is the whatever you have to multiply the input by to get the output. It's called the transfer function. I call it H. So that the transfer function H of t is equal to O of t over I of t. Its transfer function is the ratio of the output to the input, so that therefore the output is equal to the input times the transfer function. Simple. I didn't write that very well, of course. Let's do it a little lower so I can write straighter. So that the output, and that's not theta, that's an out, that's an O. I'm just making it look funny. Output of t equals transfer function. Still can't. Let's do it a little lower. The output of t equals the transfer function of t times the input of t. See? So in time domain, this is really hard to do all that. And by this I mean times. You get that right. This is times. So I have to go like, like this. Make that sure that's it. You're multiplying the two together. Yeah, you have to put a bracket around it, I think. Then notate multiplication. So here's the thing with systems engineering. I'm getting there. So what happens is in time domain it's messy, but in frequency domain, here's the magic. Input of omega into transfer function of omega, output of omega. Here's the kicker. If I change the input function to frequency domain and I change the transfer function to frequency domain, then what happens is this beautiful thing happens where what I just said actually becomes true, where the output of omega equals the input of omega times you do that times, it looks like an X though. I'm going to put a dot, times H of omega, so that the output in frequency domain equals the input in frequency domain times the transfer function in frequency domain. That's beautiful. That does not work in, I said it looked like I was saying that with time domain, but actually in time domain, it's just O of t goes into H of t, and God knows what, the input of t goes into H. We don't know what the output is. It's not so cut and dry. There's a lot of math involved, dude. It would be hard. But if you switch the input, transfer the input to frequency domain, and transfer the transfer function to frequency domain, then the output in frequency domain is just the input in frequency domain times the transfer function in frequency domain. So O of omega equals I omega times H omega. Beautiful. What do you do then? Then once you have the output of omega, you take the inverse Fourier transform of O omega to go back to O of t. Voila! Now you have the output in time domain. That's how you figure out how to process a signal with a system. Take the signal input, transfer to frequency domain, take the transfer function, transfer that to frequency domain, multiply the two together to get the output in frequency domain, take the inverse transform of the output to get the output in time domain. You have the output of the system with that particular input. And then you have something, that's basically the lecture included, basically. But let me just go on a couple of other things. There's a couple of things that have to be said, though. What about, we call it LTI, linear time invariant. Time invariant means this only works if you assume the system isn't changing over time. That's another variable. You have the same system today you had yesterday. That makes this work. If the system changes every day, it's another story. You have to deal with that harder. Next, linear. Linear means if I put an input in and I double the input, I get double the output. It's linear as far as the input-output ratio. But if I put in an input of 5 and then I put in an input of 10 and I get 3 times rather than twice, that's not a linear system. It might not work. But for a linear time-invariant system, this all works. And I never got past that in Harvey College. I never went to nonlinear, non-time invariant systems, but maybe that wouldn't have happened until I actually got a job, LOL. But that's how we start. We start with LTI systems. And anything else? Let me think of anything else I want to say about that. Just let me think. I want to add a little bit more. Then more just for fun. So we have time domain and frequency domain. Now, time domain is like position in our world. Frequency domain is like momentum in our world. And according to Werner Heisenberg, you can't know both with certainty. If you know the position of something, you can't know its momentum. If you know it's the momentum of something, you can't know its position. It's called the uncertainty principle. What does that mean for the math we just discussed? Well, let's check it out, as Chevy Chase said in Fletch, 1985, great movie. If a system is contained, if a function is contained, we know it. If a function is infinite, we do not know it. What does this mean for this problem here? Well, it means if time domain is finite, is contained, frequency domain will not be. Because if we know the time, or if we know the position, which is the time, we can't know the momentum, which means the momentum, or which in this case, the frequency domain function will be infinite, spread over the whole infinity. We can't know it. But the reverse is also true. If the frequency is contained, which is momentum, we know the momentum, then the time will be all over the place, all over the place, unknown, infinite, spread. So we won't know. We can't know the position. If we know the time, which is the position, we can't know the frequency, which is the momentum. If we know the momentum, if we know the frequency, which is the momentum, we can't know the position, which is the time. You can't know. If you have a particle in a box, you can't know where it is and where it's going at the same time. You can know where it is, but not where it's going. You can know where it's going and not where it is. It's Heisenberg uncertainty principle. That's why in Breaking Bad, Walter White shows, say my name, he called himself Heisenberg. Very famous Werner Heisenberg, great German theoretical physicist. One last little tidbit. That's a little bit of math there, a lot of math maybe. This also applies to something I've read about called quantum creativity. I won't write it. It's not my own thoughts, so I'm not going to plagiarize it or whatever. But it's true about thought as well. Think about thought in terms of uncertainty. If what you're thinking about, if what you're thinking about is the position of your thought, then your momentum, which is where you're going with your thought, what you're going to think of, how the direction of your thoughts are going, can't be known. If you know what you're thinking of, you can't know what you're thinking next or where you're going with your trend of thought is. The reverse is also true. If you know your trend of thought, you know the momentum of your thinking, you can't think. You don't know what you're actually thinking at that time. You don't know the position of your thinking. Very strange, but true. If I know I'm thinking of an elephant, I don't know what I'm going to think of next. If I know I'm thinking of scales and music, I don't know what song I'm thinking of. You can know where your trend of thought is going, but not know what your thought is, or you can know what your thought is, but not know what your trend of thought is going, where your trend of thought or where your thoughts are going. You can't know both at the same time. Just like you can't know a particle's position and its momentum at the same time, and you can't know therefore in math, if a time domain, if a function in time domain is contained, the frequency domain will be uncontained or infinite. If the frequency domain of a function is contained, then the time domain of the function will be uncontained or infinite. Love you guys. Peace, love, and rock and roll.